Good morning, class. Today we're going to be talking about applied and named forces. Throughout the rest of this week, we're actually going to be reviewing some of the forces that we've already covered, but today we're just going to start with the applied and named forces. Now, what are applied and named forces? Well, they're forces that are being applied by an object that don't follow any of the common forces. And by common forces, I mean forces that have their own formula or commonly show up and have specific names. So I'd be talking about things like gravity, for example. It has its own formula and it has its own specific thing. Friction is another example. And normal force is another example. These are not generally considered applied or named forces. They're forces that have a specific uh, use and they are specifically a particular thing. So what could be things that are applied or named forces? Well, it'd be any force that's applied that isn't one of those usual sort of things that are already something, such as an engine on a vehicle is pushing. That would be an applied force, F engine, right? Or if Steve is pushing something, I could call that F Steve. These are named forces. I could also call either of these F applied. It's the same thing, and it doesn't really matter what I call them. So that's what an applied force. It's a force, just any force applied by something that isn't one of the things that we already always use all the time, like gravity, friction, normal force, or maybe springs. So there's no set formula for them, so how do we deal with them? Well, first we start with free body diagrams. What do we do when we are doing applied or named forces with free body diagrams? Well, you start by drawing your object. So Jeff is pushing a box, right? So here's our box, and he's pushing it to the right. We could label this force either as the Jeff force, F Jeff, or we could have labeled it F applied, because Jeff is applying a force. Either one of these is correct, because they are talking about the same thing. And it is 30 newtons, so force Jeff is 30 newtons. The applied force is 30 newtons. They're the same thing. But it doesn't need to just be individuals, right? The car engine pushes it forward, so here's ourself a little car. And here's the front windshield, so pushes it forward to 3,000 newtons. What could we call this force? Well, you have a couple options. You could call it the engine force, right? F engine. Or, as before, you could also call this the applied force. It's 3,000 newtons, right? Are these the only two names? No, you could give it other names. You could call it force car. Whatever, it doesn't matter. The key here is that it's just another force, and calling it applied or engine is just a matter of naming. Let's do one last example. This wind is pushing a duck 450 newtons, 30 degrees south of east. Well, here's my duck. It's just a box. And 30 degrees south of east, well, east is going this way in the dotted line. So south of it would be a little bit down, like that. 30 degrees south of east. Now, is the wind force something that's a usual force, something that's calculable? Is it like gravity? Is it like friction? No, it's not. There's no way to just calculate the amount of wind. So it gets its own name. It's force wind. All right, force wind is 450 newtons. Could I have called it the applied force? I definitely could have. It doesn't matter. In each of these cases, you can see that you can name the force specifically, or you can call it the applied force. It doesn't matter. So applied forces and named forces are the same thing. Let's work on trying to apply them. And we always apply them using a net force equation. So how do we make net force equations? Well, step one, make your free body diagram. That's always step one. Step two, you ask yourself which way it accelerates. the net force equation will only uses the forces that are in the parallel direction of motion. So that only uses the forces that are parallel. Here we go, to the direction of motion. So if I was pushing a box, for example, this box might be going to the left. But if there was friction, friction would be pushing to the right. So I would include both of those forces in my net force equation. But if the box is sitting on the ground, gravity's pulling down, normal force is pushing up. Those aren't in the same direction. Those are in fact perpendicular to the acceleration. That means they'll end up balancing. And if they didn't balance, well, the acceleration would go in that direction. So that's fine. Then you go ahead and you determine which forces are working together and which forces are working against each other. So we're talking about winning or positive forces, or losing or negative forces. Again, winning, losing, it's not important which one's which. What is important is that you make sure that in your net force equation, you keep each force separate. Don't try to lump them all together into one winning group, one losing group, because that's where you might end up making some mistakes. All right. Now that we've looked at making equations and making our free body diagrams with applied forces, let's try a couple problems. So here we go. There's a little thing that's missing here, so I'm going to make an adjustment as we complete this. Let's read the question. A 12-kilogram box is sitting on a frictionless table. Jerry pushes the box with a 3 Newton force to the right. Let's just add in some direction so we don't get confused here. So he pushes with a 3 Newton force to the right. So let's determine the acceleration of this box. Well, step one is, as always, our free body diagram. This box is on a table, and whenever I think of boxes on tables, I'm pretty sure that they're on Earth. So that means there's probably some gravity. Now, the box is on a table, it's sitting on a surface, and if it's sitting on a surface, that means there's got to be some normal force keeping it from breaking through that surface. So there's our normal force. Sorry for the bad drawing there. Oh boy, that was really bad. Much better. Well, not much better, just a little bit better. But then there's one more force. There's the force of Jerry. He's pushing it to the right. So F, what do we call this? Should I call this applied force? Should I call this Jerry force? Doesn't matter. I'll go ahead and call it F applied in this case. Force applied is 3 newtons. Now those are the only forces because I see that in the problem it says it's frictionless. So let's make our net force equation. The net force equation, F net, is the sum of all my forces. But now I've done step one, my free body diagram, I take a look at step two. I ask myself, which direction is this accelerating? Well, it's probably not breaking through the table, and it's probably not leaping up. The most likely direction of acceleration is, well, to the right. That's probably where it's going. So if that's the case, then all of the forces that are parallel, like the applied force here, are going to be in my net force equation. These ones that are perpendicular, the normal force and the gravity, well, these ones, they're going to balance. And if they balance out, I don't need to include them into my net force equation because they are perpendicular to my direction of motion. So with that, that means my net force equation is simply the applied force. Well, that's pretty easy then. Let's go ahead and finish solving this. The net force always can be separated into the mass times the acceleration. So the mass is 12 kilograms. The acceleration is the thing that we're trying to find out, and the applied force here was 3 newtons. So to solve for that acceleration, we need to just divide both sides by 12, because that'll isolate for the A. And the acceleration here we see is going to be 3 divided by 12. That turns out to be 1/4. or 0.25 meters per second squared. And this is going to be to the right. Now this is just one of the simplest questions that we can do with the applied force. Let's go ahead and try one with a little bit more on it. All right. One thing that I notice about this problem is that the numbers don't work out nicely. Let's go ahead and let's adjust things just a little. I'm going to change this into a 10 kilogram boat. There we go. A 10 kilogram boat is traveling on the ocean. The engine provides 200 newtons of force heading north, and an ocean current pulls the boat with 40 newtons directed south. The boat is accelerating at 5 meters per second squared in the north direction. Determine how much drag the boat experiences. This is a fair bit more challenging. There are a lot of different forces, and in fact, 3 of the forces are all applied forces. There's the drag force, there's the current force, and there's the engine force. How am I going to differentiate them all? Well, I'm going to go ahead and I'm going to make north go to the right and south go to the left. Let's make a free body diagram. Reading this, I know that my engine, F engine, is 200 newtons. Now, why did I call it engine instead of applied? Well, I called it force engine because I noticed that there are 3 different applied forces, and so I'm going to choose their names rather than calling them all FA, because if I did that, it'd be incredibly confusing. Now, the current is pulling to the south. F current. Thinking more on this problem, what else is there's drag. Well, what's drag going to do? Drag is just like friction. It's going to resist motion. And it says that the boat is accelerating north, so it's pretty safe to assume that the drag is going to be going in the opposite direction. F drag. Are there any other forces on this situation? Well, you might argue, Mr. Westergaard, boats on oceans happen to be on Earth. That means there's got to be some gravity. And you would be right. There would definitely be some gravity. Now, what keeps boats from sinking down into the ocean? Well, that's got to be not a normal force. It's got to be buoyancy. I'm just going to call it FB for F buoyancy. Now, I'm going to make sure to put all the numbers that I absolutely know. For example, this current here, I know it's 40 newtons. That's all the numbers I absolutely know. Let's ask ourselves a question, because step 1 is done for our net force equation. Our free body diagram is done. But let's ask ourselves the question, what direction is this going in? Well, the boat accelerates to the north at 5 meters per second squared. So that means the direction is north-south. Those are the parallel directions. Anything perpendicular, like up-down here, is going to balance, and we kind of get to ignore it when we're talking about our net force equation. So what is my net force equation going to look like? Well, I consider all my winning or forward or successful or positive forces. Force engine, right? That one's clearly the winner. And then I consider all the forces that are working against it. So something like the current is working against it. So I'm going to minus force of the current. But I also note that the drag is working against it as well. F drag. Now that's a complete net force equation. It has all of my forces, and it's going to be working out now. We can use this to solve. Let's plug in our numbers and the things that we know. Well, I know net force can always be turned into mass times acceleration. So the mass is 10, the acceleration is 5. My engine force I know is 200. My current force I know is 40. And my drag force is unknown. I don't know what it is. time to do just a little bit of calculator work. 10 times 5 is 50. 50 equals 200 minus 140 is 160 minus forced drag. And then to solve for that, we can just see that 160 is a positive value being added and subtracted. So I will subtract 160 from both sides. Subtract 160 from both sides. That'll eliminate that. That'll eliminate that. That leaves me with negative 110 is equal to negative forced drag. Now they're both negative, so it clearly shows here that forced drag is going to be 110 newtons. Which direction was the drag force going? Well, we just take a look back at our free body diagram and we can see here that the drag was heading in the south direction. So force drag is 110 newtons to the south. There we go. And that solves that problem. I hope you found this to be a helpful review of what are named and applied forces, and a little bit of review on how to make your free body diagrams and how to make your net force equations. Have a good day.